I brought a couple of slides from previous class, so just to refresh your minds where were we, what were we talking about, right? We were talking about tangent normal coordinate system, right? Generally speaking, we are looking into curvilinear path. Like how do we analyze or how do we find position, velocity, and acceleration for a curvilinear motion, right? First, we used Cartesian coordinate system or Cartesian coordinates, like x, y, z technically to be more general in three-dimensional space. Now we're talking about tangent normal coordinates, right? The coordinate system that is basically uh, defined by two unit vectors, et and en, et being the unit vector uh, tangent to the path at any given moment wherever the particle is, right? Tangent to the path of the motion at that point, at that moment, and en, which is basically normal to the path. So using these two unit vectors, we define a new coordinate system. In this coordinate system, we found velocity, followed the definition for velocity, and we said velocity is v et, velocity, whatever the magnitude, multiplied by the uh, tangent unit vector, et. So the velocity is always tangent to the path, whatever the path is. And we said, well, magnitude of velocity is nothing but ds dt. So ds dt et. We defined also acceleration, like just basically taking derivative with respect to time from velocity. But there was a little bit of trick there. How do we take derivative of et with respect to time? So det dt, I told you, is d theta dt en. You can, if you want to, this should be at there you go. You can take a look at your book. There's more details on how to prove that. But it's good enough for us. As long as you apply that, you get the definition for acceleration. Acceleration it has two components. It's not like velocity that's just only tangent to a path. Acceleration has two components, one tangent to a path and the other one normal to a path. The tangent component, whatever is multiplied by et, is dv dt, derivative of velocity with respect to time. Normal component is v d theta dt, right? Theta being the angle et creates with horizon, right? Horizontal line. Now, uh, there is another way of representing this acceleration. Velocity is just velocity. There's another way of representing this acceleration, or better to say the second term in the acceleration equation, d theta dt, v d theta dt. And that is what I'm going to talk right now. So if I draw the path here again, let's say this is the same path, and we are this, let's say it's the concave side, and the other side we have, let's say this is the, that is huge. Somebody's gonna change it. So this is, let's say, the radius of this, right? If you think of this as a curve, like it's part of a curve, this part, this has the radius of rho. If this angle, let's say this is the center of whatever this curve is, this is the center for that portion of the curve. If we move d theta, if you call this d theta, the change in angle, this one, and we call this ds, or refer to this as ds, change in the position, right, along the path. Remember, this is theta. This is theta. This is theta, and this is theta plus d theta. So we have d theta change. And the particle is going from point here, this is p at t, and this is p t plus delta t. Just following the particle on this path. Now from geometry, right, we know ds is equal to rho d theta. The length of a curve is pretty much the multiplication of the radius by the angle in radian. Right? Hopefully you remember that from somewhere. If you don't remember that, it's fine. Just take my word for it. Um, so the length of the path is equal to the radius multiplied by the angle, right? In radians, obviously. Now, this is given if you just multiply this by dt from both sides, or you can think about it taking a derivative with respect to time. I don't put it here, so it depends on how you look at it. Would be ds dt is equal to rho d theta dt. Right? Now ds dt is v. We know this from before, that this is the fundamental definition for the magnitude of velocity. So this is v. See what happened there. So d theta dt becomes v over rho. Now I'll take this, I take what I got here, this one, and plug it into the equation I had from before. Now I get a new form for the equation for acceleration. I'll get a as a vector. Well, the first term doesn't change, dv dt et plus, if I plug that in, this becomes v squared over rho en. This is a new form. Let me be consistent and change the color to what we're using for equations. All right. So it's a new form. First term, tangential term, is the same. Normal term changes v squared over rho. As long as you know the velocity at the magnitude of the velocity and you know the radius, as it's called, radius of curvature, right, you are able to find the normal component of acceleration. So rho here is, let me write it here, rho is the radius of curvature. Right. So to just sum up, your acceleration is going to have two components. We call this first one AT, tangential component. If my tool works here, somehow it got stuck. This happens more than it should. No. I am working on this, folks. I totally lost the, so hold on. Sorry about that. Hopefully they're still there and they're saved. Just giving up on me. Oh, they are. Almost. Let's see if things are working. Yep, not bad. All right. Let's go back to what we were doing. Sorry about that. All right. I just only lost the row, definition of row. So I'm just going to add it here. That's radius of curvature. So basically, you're going to have two components, right? This is, you can write it as AT component of in tangent direction, ET, plus component in normal direction, EN. And then AT would be dv dt, and AN would be v squared over rho, right? Now, if when you write it this way, just remember that this is normal component, normal component, v squared over, it's v squared over rho. Yeah. Since v over rho, if you plug it back to equation, we already had a v in the back here. And so v multiplied by v over rho becomes v squared over rho. So this is tangent component. Just one thing, pay attention. As I mentioned before, when you are looking at a specific, let's say, motion on a curve, at any given moment when you are trying to find ET and EN, well, ET is pretty straightforward. It's always tangent to the curve, right? ET, this is ET. Now, normal component, well, let me move it a little here so I can make the point that I want to make. Normal component is the unit vector En, better to say, should always be defined at the point in a way that it's pointing toward the concave side of the path. So in this case, this is En. This is the concave side. This case, this is En. This case, this is En. Right? So depending on how, if you had, if this continued, let's say this way, then at this point, you again had your ET tangent and then En towards the concave side. Let's just remember that when you are finding ET and En. Right? That's pretty much it. So all you need to know is that when you are in this component in coordinate system and you're looking at motion on a curvilinear path using tangent normal coordinates, that's how you define your velocity, acceleration, tangent normal component dv dt. Tangent component can be defined as v d theta dt or v squared over rho, rho being the radius of curvature for the path that your particle is following. A few couple of things before we wrap this theoretical part and look into examples. First is we can write this in xy coordinate system in a very easy way, right? If you think of this as xy coordinate system as before, I mean, this is x, this is y, Cartesian, and then you have your let's say your path is something like this. Oh, that's not what I wanted. Your path is something like this. I can do better. Your coordinate system ETEN, let's say, at this given point is like this, ETEN. And this one is theta, right there. You can write this, write ETEN in Cartesian coordinate system. Pretty straightforward. If you think of this as I and J, if this is I and this is J, we're going to write the unit vectors in different coordinate systems. So your ET becomes cosine theta I, if you look at that triangle right there, I don't want to make it crowded there, plus sine theta J. And your En becomes minus sine theta I plus cosine theta J. So this is basically a relationship between these two coordinates. You'll still go over an example maybe next class. We might not be able to cover it in this class. That how we convert that. It's pretty much just looking into the triangle there. You know the angle theta. You know one side. You want to find the hypotenuse, or you want to find the adjacent, depending on what you're looking at, and you can just go from one to another. As long as you know theta, you're just good to go, and you can make the conversion. So this is the, let me just point it out, a relationship between Cartesian and tangent normal. I'll just write it this way. The last thing is special case. All right, so now we know how this, what are the definitions of velocity and acceleration. Remember, we're talking about position, velocity, and acceleration. Now we know what are the definitions for velocity and acceleration in this tangent normal coordinate system. Now, a special case that we are also interested is when this curvilinear path is just a circle. Right? It's called you can just put it on the circular motion. Right? Circular motion is basically a special case for curvilinear path. So I'll write it as special case. Put it this way. Special case circular motion. So if we have, let's draw a circle and look what happens there. If we have a circle like this, and we are looking at, well, let's say just some random, this is point O, is the center, as close as I can to be center, into center. There you go. This is point O. And let's say the particle starts the motion from here. It's motion from here. It goes this way, gets to another point. And this is theta. And the radius for this circle is r. So if a particle moves in a plane circular path of radius r, it's going this way. Now this is S. Remember, this is the path that we said the length of the curve is equal to radius multiplied by the angle forming that curve. So this would be S is equal to r theta, similar to what I used to derive the equation. Right? This is just given. Right? This is not from dynamics. This is what we know already for a path. As long as the theta is in radians multiplied by r, it gives you the length for the curve formed because of that theta motion. Now, if you take derivative with respect to this, this is ds dt, again, the same story, r d theta dt. Right? This we can define as, now this is where I wanted to go. So this is v, or ds dt is v. I'm going to define d theta dt as omega, angular velocity. So this becomes v is equal to r omega. Omega is also a vector, but you'll see later. So this is the velocity when we are we have a motion on a circle. Now, what is the difference between this one and the previous one? Well, the previous one we just defined dv dt for velocity here. We defined ds dt et, right? Now, in this case, it's always let's go back there. The velocity is always tangent to the surface wherever we are. Let's say I am somewhere here, right, this point. So this is your velocity. If you were somewhere here, this is your velocity. It's always tangent to path. The same story as a curvilinear, but here it's a circle. So we don't even use ET, I would say, for at least for velocity. So anywhere you are, you already know that it's always perpendicular, or sorry, tangent to the path. So let me just write it here just in case. Omega, we define it as angular velocity. It's a new term. With unit. Now, what is the unit of angular velocity? You might have seen it before, so just checking.
Radians per second?
Exactly. It's radians per second. Thank you. So omega velocity, the unit is always displacement over time, right? Now, displacement in the case of a circle moving around a circle, you can think about it as radian, how far you go. So this is radian per second. I mean, it can be the variation of this. Any variation of this, it can be radian per second, can be radian per minute, right? It just has to be the unit you measure for the angle over the unit you use to measure the time. So radian per second is pretty standard. Radian per minute can be degree per second, can be degree per minute, it can be degree per hour. So any unit that you use to measure the angle goes on over any unit that you use to measure time can just be the unit for angular velocity. Now, if we take another derivative, remember, we are in this special case right here on a circle. If I take another derivative to get to acceleration, right, acceleration would be a, let's see, write it, I'll say a is equal to r d omega dt. Now, I'll define this as alpha, d omega dt as alpha. So this becomes r alpha. Now, this is the component of acceleration, tangential component of acceleration. We are taking derivative, we are not taking into account any unit vector, nothing, right? It's just v perpendicular, tangent to the path. We take derivative of that, it's going to give us the tangent component of acceleration. So I have to put at. You can write it in a better, more neat way, r alpha. Write it this way. So it's the tangential component of acceleration in a circular motion. And we defined alpha, I'm just going to be consistent with what we were doing, alpha as angular acceleration. With unit, any unit that you use for measuring the angle over time squared, it's acceleration, right? In a linear motion, you have meter per second squared. Here, you are going to have a typical one, radian per second squared. Can be radian per minute squared. Can be degree per second squared, depending on whatever you use for measuring the angle over whatever you use for measuring time squared. Now, standard one is radian per second squared, obviously, in both of these. This is the standard one, and this is the, or better to say SI unit, but the others can also exist, and you have to convert from going from one to another. Now, this was just the tangent component. Right? If I have a circle like this and I have a motion, I have to take a look at both. Right? If I have a point P there, this is going to have a tangent component. That's a very, so AT. And remember, concave side. So this is going to be AN. if this is the circle, it's pointing to the circle of this curve, right? Wherever the center of that part of the curve is. So we're going to have a normal component as well. I can think about AT, well, think about AT, not you can. Think about AT as the tangent component of acceleration and AN as the normal component of acceleration. So to find the normal component, we can use what we had before, right? We said right here, we said AN is V squared over rho. Now in this case, rho, well, rho we said is the radius of curvature. In this case, radius of curvature is nothing but the radius of this circle. So I can write AN as V squared over R, just replacing rho with R from before. Now, since I know V is R, let's just not use vector notation for now. Since we know V is R omega, I can just replace R omega in the new equation, like V squared. If I replace V with R omega, right, squared, this gives you R omega squared. So AN can be V squared over R or R omega squared. Either one works. Therefore, so acceleration would be AT ET plus AN EN. With AT and AN we defined before. So again, here is what we did. We basically look at a special case, circular motion. Right? We said, well, that's the general form we talked about for a curvilinear path. What happens? We have a tangent component, normal component. Tangent is always tangent to a path during the motion. Wherever we are, normal is normal to a path, and normal obviously as a result to ET. This angle is 90 degrees there, needless to say. And it's always pointing towards like concave side, right? In the concave side, pointing toward the concave side of the path. Then we said there is a special case for circular motion. We found what is the velocity in circular motion. Typically, that R, well, not typically, always that rho that we define as a radius of curvature becomes R because it's fixed. Right? In a typical path, that rho changes, depending on where you are, the radius of that curvature, because the curvature changes. In a circle, it's just R. We said V is R omega, omega being angular velocity, which is nothing but d theta dt, right? Radian per second, radian per minute, whatever unit you use. And the acceleration became, it has two components, tangent and normal. Tangent is, I should have put it that way, R alpha, R being the radius of the circle, alpha being the angular acceleration, which is basically the derivative of angular velocity with respect to time, or we can think about that as second derivative of angular displacement theta with respect to time. Plus AN EN, normal component can be defined as V squared over R or R omega squared. Either works. All right. Now, if you want to get a just comparison and keep it in mind that what happened there, you can also make a comparison between a straight line motion and circular motion to see that pretty much they are the same. We only changed acceleration with we changed the velocity. We gave it a name omega over there. Velocity was ds dt here. Omega. Let me just write it. So omega for straight line we had V. For angular, so circular motion we had omega. Now we had acceleration, and here we have angular acceleration. So there we said is ds dt. Here we say is d theta dt. Over there we said is the second derivative of displacement with respect to time, or the first derivative or derivative of velocity with respect to time. Here we say second derivative of theta with respect to time, or derivative of omega with respect to time. One small thing you can add here, remember there was this, I would call it golden relationship, that sometimes really comes in handy and it helps, was that in straight line motion, we had VdV is equal to AdS. Now you can copy the same thing for circular motion, replace V with omega and A with alpha. Omega d omega is equal to alpha d theta. To just get a direct relationship between velocity and acceleration, angular velocity and angular acceleration for circular motion. Just to make a comparison, to give you a sense that if you want to compare the straight line motion with the circular motion at least. Remember, circular motion is a special case of the motion on a curvilinear path. All right. Question about this before I go into examples. Go ahead, Bobby. Second column next to alpha. This should be d theta squared. D is this. Maybe that's the problematic one. Yeah, okay. Yeah, I know when I write in a way that is almost impossible for myself to read. All right, so maybe that's better. Yeah, these are all dt. Right. All right. Let's take a look at an example, or a couple of examples. We'll see how many we get to do this in this class, and we'll do whatever is left in next class. If my all right. So, example. Example. We have the problem statement goes as this: the angle theta is equal to 2t squared radian if if the angle theta is equal to 2t squared radians, or radian, what are the angular velocity? Start with easy one. Angular velocity and angular acceleration of point P. I can replace point with particle in terms of tangent and normal components when P has gone 1 revolution around the circular path around the circular path. That's it. I'll be able to say add this path starting at t equals to 0. So we know the beginning is t equals to 0. So let's see what we got there. Well, we're looking for angular velocity and angular acceleration. Now, we just go back to definition. And remember, this is a circular path. A few things that you have to pay attention to. And this is circular path. Right? So, what are the definitions that angular velocities are what I need to find? Omega, and I have to find alpha. Let's go back. Circular motion. So I have omega as the function of theta with respect to time, as derivative of theta with respect to time, and alpha as second derivative of theta with respect to time, or derivative of omega with respect to time. So what does that give me here? What is omega, and what is alpha? For now, forget about the time or anything. Just give me the equation for omega and alpha.
Omega will be d theta dt. D theta over dt.
D theta over dt, exactly. And that becomes?
D2t squared over dt.
Well, if, well, yeah, you're really avoiding the t squared, but it's technically correct, dt. And that becomes? Come on, folks, it's derivative.
4t.
4t, exactly. All right. Thank you. And then we get second, or we can just take the derivative with respect to omega. The omega dt, what gives you just 4. And I'll go with radian per second and radian per second squared. So pretty much it tells me that alpha is constant during this motion, right? It's always 4. Omega is 4t, meaning that it's a function of time. So depending on how long has it been that we started the motion, omega, changes. All right. I have to add something to problem statement. Angular velocity and angular acceleration. Sorry about that. I'm gonna open it right here, as well as velocity and acceleration. That was a very long add. So what are the angular velocity and angular? What are the angular velocity and angular acceleration, as well as velocity and acceleration? Meaning that, well, we found velocity and acceleration. Now we have to find velocity and we found angular velocity and angular acceleration. Now we have to find velocity and acceleration. Let's see, how do we do that? V is equal to, remember, it's a circular path. So this is V, this is A. I'll just put the, let's not just put the vector there. VA. I'll go with, I guess, the vector definition. So what are V and A? If we go back to what we had there for circular motion right there. V is R omega. We already know omega. Yeah, I didn't give you R. That is part of the problem, what I'm putting here. So in case you were wondering that, how do we calculate this without R, is because I didn't give you R. This is R is equal to 4. And let me be more. R is equal to 4 meters. So velocity becomes R omega. R being 4, omega being 4t, this becomes 8t. Well, no, 4. How did I get 8? 16t, right? 4 times 4. Since I put a vector, I'll write it as ET. Just a small thing to remember, that if you mention that as a vector, I'm going back, just make sure we're on the same page. Right here, if V is as a magnitude is R omega, but if you want to write it in a vector, or V as a vector is R omega ET. Right? It's always tangent to path, so you can just write it as R omega ET. Either way, as long as you know that R omega is tangent to path, you're good. But if you represent it as a vector, remember to put ET there. Hopefully that made sense. I jumped back and forth a little bit. Just remember, V is always tangent to a path when we in any curvilinear motion, including a circular path, motion a circular path. So when you write it as a vector, remember to put ET to represent the direction. Remember, a vector has magnitude and direction. So always have to take into account both when we are writing things as vectors. That becomes 16t. Right? And if you want to be very meticulous, you can also put the unit here, meter per second. So acceleration, well, has two components, AT, ET, plus AN, EN. All right, component in tangential direction, component in normal direction. Now, I usually write it this way. AT is R alpha, and AN is R omega squared. Let's go with omega squared instead of V squared or R, because that's probably a little convenient. So R alpha is, R is 4, alpha is 4. Well, this becomes 16 meter per second squared. This is R omega squared, so 4 times omega is 4t squared. So 4 times 16, 40, 64. This becomes 64 t squared meter per second squared. So this tells me that A, for acceleration, is 16 ET plus 64 t squared En. So just identify the things that we found. We found angular acceleration. We found angular velocity. We found angular acceleration. We found velocity. And we found acceleration. There must be a hat here, since this is the unit vector. Now, here is the tricky part, that the problem is telling me that, well, this is good. I found everything as a function of time. Now, the problem is telling me that what are these values, like omega, V, and alpha also, A, when this particle goes around this circle 1 revolution. So it starts on this side, it starts here, goes all the way and gets back. So 1 revolution, right? 1 revolution. That's what is mentioned. 1 revolution around the circular path. So what do I do here now? Now I need to find t. To be able to plug it back to these equations, I need to know how long does it take to finish 1 revolution around the circle. Because if I don't have t, I can't find omega, I can't find v, and I can't find a, because the normal component of a is a function of time. But I'm not given the time directly. I'm given this piece of information that the motion is 1 revolution around the circular path. And it starts from t equals to 0. So whatever, how long does it take? It's just the time. There is no initial time. The initial time is 0. How do I go from knowing that um, the particle moved 1 revolution around the circular path to the time that it took for the particle to take that path. S, what is S? Yes, Francesco, that's exactly where I'm going. Exactly, Samuel. So S is not r theta, right? We have a circle. So in terms of a circle, when you go 1 revolution, is basically just your path is 2 theta, right? The perimeter of a circle. So you know your path. Right? So let me write it here. 1 revolution means theta is 2 pi. Right? This perimeter of the circle. Now I know the relationship between theta and t, as Francesco mentioned, right? I know that theta is equal to 2t squared. Always pay attention to problem statements. 90% of the time, things are missed because we're not paying attention to problem statement. So theta is 2t squared. This means that this is equal to, or maybe I'll write it this way, so later on, if you look at it, it makes more sense. Theta is equal to 2t squared. The result, 2t squared is pi. So you'll get your t squared as pi. Or you can think about it as t as square root of pi. Second. So this is the time that it took for this particle or point to finish that 1 circle. Once we know time, the rest is straightforward. I just plug in. Right? Once we know time, you can say, well, now the velocity v is equal to 16 t. So this means it's equal to 16 square root of pi et. I have to remember, since I'm representing as a vector, 16t et. This is second, meter per second, it's velocity. Acceleration, well, the first term, tangential term, has nothing to do with time, so it's still, this is just basically 16 et. The second term, t squared, that's a very, well, remember, this is, let me see the question, what happened to 2 and 2t? Well, this theta was 2t, 2 pi, right here. So that 2 was just canceled out. I see where the confusion coming from. Well, I didn't put the 2 here. There you go. My bad. There you go. Now it's easier to follow. I forgot to put the 2 there. All right. So this becomes 16 ET plus, well, that's 64 t squared is just pi. So this becomes 64 pi en, meter per second squared. This is the final thing that, these are the final expressions that I was looking for. Because I was asked to find velocity and acceleration, you can find the angular velocity and angular acceleration the same way. Angular velocity becomes 4 times square root of pi radian per second. Angular acceleration doesn't really change. It's still 4 radian per second squared. Right? Question on this one. It's a good question. So when we do dimensional analysis, radian as a unit, you can think of it as no unit. I think that's the best way I can put it. But yes, radian does not come into, when you do dimensional analysis, radian or degree, you can think of it as no unit. Whenever you're doing dimensional analysis or you're multiplying things. So over there, alpha is radian per second squared. Think about alpha radian as no unit. So meter per second squared. Right? Or r omega, right? Radian per second, think of radian as no unit. Becomes meter per second. That will always get you to the right place. If you do dimensional analysis later on, maybe they just go into details, but that's all you need to know as far as I'm concerned. That if you don't get confused with the unit, that's a good question. Don't get confused with units. Whenever you have radian or degree, you can think of that as doesn't come into play as a unit when you multiply it with other things, or it comes when you're looking at how to find the unit for a specific equation, including some kind of angle. All right, as I guess the easy path to go and how to deal with that. Hopefully that answered the question at least to some degree. I don't know if I answered that, but I can tell you that you can just assume that it doesn't exist, and that always gives you the right answer. All right. I do have a couple more examples. We have 6 minutes. Can I do this one at least? Let me just at least do this example. One quick example. I just want to mention that. So example, we have, it says find the maximum speed for each car. I'll draw something. If the normal acceleration is limited to 0.88 g meter per second squared, g being the acceleration due to gravity. So this is what it's given. If you think about this as part of a road, we have a car there. I don't even know how to draw a car from the top. This is top view. And we have another car there. And this is where the center of this curve is for this road. This one is 21 meters. And it's car going this way. This is going this way also. And this is 16 meters. So the information given is the maximum normal acceleration. Normal acceleration is AN is V squared over R. So if I write this, let's say this is car A. Which one I should call A? Let's call this A, let's call this B. So if I move things around, VA becomes the square root of, I'll just write it for A, RAA, right? Or better to say A normal A. And VB is the square root of RB, A, and B. I'm going through this by just writing because I want to give you time for the quiz. So VA, right? You have everything you need. That's pretty much. RA is 16 times 0.88 G, and VB is square root of 21 times 0.88 G. V is maximum. looking at these relationships, this one and this one. V is maximum when AN is maximum, obviously. AN is this is given as maximum, 0.88 G. So I just plug it in back. The only difference between these two cars is that the radius is different. So the first one, VA, becomes whatever is the radius of curvature for car A times normal acceleration, maximum normal acceleration for motion in this for this car is 0.88 G. The second one is the radius, again, multiplied by maximum acceleration. So maximum acceleration is given, radius changes, and I just use the relationship for normal acceleration, normal component of acceleration. If you do the first multiplication, this should give you 11.75 meter per second, and the second one should give you 13.46 meter per second. That's pretty much it. That's a short example I wanted to show. Can go either way. Question on this one. Sorry, I didn't really wait for you to participate in this, but I want to have time for the quiz. So, and you can always ask questions about this in the next class. Right now, any question on this? All right, let's